Today we are going to focus on the inductance part. We had eddy currents, last class period, and mutual inductors. So now we're going to look at a self-inductor. Last class period I did talk about Joseph Henry and his self-inductance idea. Here's some pictures of inductors you find in life. Now this is not a high resolution picture, I'm sorry about that. But you see things like this. Oftentimes your inductors look something like this or this, where you see a coil of wires. This top one, you can tell what's going on there. You have something wrapped up. What's wrapped up? Inside of that, there is an iron ring with a bunch of wires wrapped around the iron ring. And then there's more complicated inductors here. As you can tell by looking at these, the key for an inductor is always wires wrapped up. Here's our symbol for an inductor. That's supposed to indicate that you have wires wrapped up in a loop. Now, if you look at that symbol for the inductor, it looks reminiscent of the symbol for a resistor. So that's why we have to be a little careful in drawing our resistors versus inductors. The resistors need to have two sharp angles. The inductor has only one sharp angle. That's how you differentiate. So make sure you're careful, for instance, in lab next week, about how you draw an inductor versus how you draw a resistor. Inductors, the symbol for the inductor is L. I don't know why. We can't use I because I is current. So it's inductors, probably from another language that I don't speak. So let's learn about these inductors, these self-inductance devices. So the definition of inductance is right there. Isn't it nice having a new tip so it doesn't skip and jump? I'm very pleased with the new tips. So what is N? N is the number of turns or number of loops, depending on who you are. Most textbooks use the word term or turns. What is the name of that symbol? Okay. Phi or phi, but not fo or fum. And what it stands for is what you were saying. The flux. Well, we've done two kinds of fluxes. It's important to have the right flux, and this equation doesn't show which flux it is. Which flux is it going to be if you're talking about self-inductance? Self-inductance, by definition, is you have a current flowing through the coil and it creates a voltage. It's going to have to be the magnetic flux. Because we're using Faraday's law of inductance, which uses the magnetic flux. L, I just said what L is, so remind me, what does L stand for? Inductance. And I is current. But I'm not writing those down because I know you've got those down already. The SI unit for inductance is the henries, named after Joseph Henry. And so we can figure out the units just by taking this relationship and saying the units for henries. This is actually technically how you show units of, is equal to units of turns times the units of magnetic flux divided by the units of current. What are the units for turns? It actually turns out there's none. We use turns to say 1 loop, 2 loop, 3 loop, 4 loops, but there's no units for it. How about magnetic flux? Tesla's magnetic field, magnetic flux is current through the magnetic field, or not current, magnetic field through an area. So it's going to be Tesla's times area. We have a name for that. It's a name I usually emphasize, the Weber. So the unit for the magnetic flux is the Weber, hence the WB here. I kind of like the Weber just because it's similar to my last name. A lot of Webs do come from Webers if they're Germanic Webs. I am a Welsh Web, so mine comes from more W-E-B-B-E. In case you're curious, turns out I'm not related to William Shakespeare. No, his grandmothers, both of them were Webbs, and it was thought that most American Webbs were descendants of their brother Alexander, but turns out I'm not. I did DNA testing. Yeah, I know. Apparently, I had a different relative who made fishing nets. Anyway, yeah. Your last name means something, and for most of us, it's not something all that exciting for what our ancestors did for a job. Other people, you have different naming conventions. But anyway, so to this. So we have the Weber is a Tesla times a meter squared. And so I could put that in or just leave it in Weber. So the easiest unit is the Weber per ampere. Or I can put Webers per second divided by amperes per second if I want, and then, get something different. But let's just stick with this one for now. Weber per ampere, the unit of the Henry. So how is this useful to us? Based on that definition of inductance, then I can use Faraday's law of inductance and say, well, if I take the change in the left-hand side divided by change in time, that should be the induced EMF. So from Faraday's law of induction, there's Faraday's law of induction. If the number of turns is constant, then that would be the same as minus the change in N times the magnetic flux over change in time. But since N times magnetic flux is defined as the inductance times the current, over change in time, if our inductance is not changing. So notice I've gone through two ifs. If the number of turns is constant, and if the inductance is constant, then that is equal to minus L delta I over delta T. And so the voltage drop across an inductor, and of course that's the same as this equation here. The voltage drop across inductor is proportional to the rate at which the current is changing. If the current's changing faster, you're going to have a bigger voltage drop. If it's changing more slowly, you're going to have a smaller voltage drop. And of course, it's proportional to the inductance. Now, if we look at how a solenoid is built, what is a solenoid? What's the physical description of a solenoid? It's a coil of wire. So if I look at a solenoid, and I can draw one here. And it's going to have a length that I'm going to mark with a lowercase l, using a lowercase l so we don't get it confused with inductance, capital L. And it has a number of turns, capital N. And if it has air in the coil, then I can do some quick calculations. I can say if I have current flowing through this, then I'm going to have the magnetic field is mu watt, number of turns per unit length, times the current. That was a result that we got from applying Ampere's law to a coil. Remember when we did the loop that went through the center and then out to infinity? Applied Ampere's law on each side of that rectangular loop. Well, if that's the magnetic field, then the flux, your area is like this. And the magnetic field is produced is going to be the same direction. So the flux is going to be B times A because they're parallel to each other. Hence, mu watt N I over L times area. And then using Faraday's law, the induced EMF is minus N change in magnetic flux over change in time bringing out all of the constants. I have that. And so I can take this and say, this piece right here, which is N squared mu watt area over length, or if you prefer, N squared mu watt area of a circle is pi r squared. And that's equal to the inductance. So we can calculate the physical inductance for a coil of wire in exactly analogous method to how we calculated the capacitance for two parallel plates. So it's proportional to the number of turns in the coil squared. So if I get more turns, higher inductance. Proportional to the radius squared. So if I make it have a bigger radius, it's going to have more inductance. Inversely proportional to the length of the coil. So if I make my coil in a shorter length, it's going to increase the inductance. Then there's one more thing in there, the mu sub zero. What is the mu sub zero again? It's the permeability of free space. It's telling us about how magnetizable vacuum is. Well, if you put something in there like iron, we saw that the iron was like 1,000 times more magnetizable than air. And so if you put iron in there, it's going to increase the inductance incredibly. Now, I'm not going to do it for calculation because it becomes just a little complicated, because this equation, the induced EMF, has to do with how quickly the current is changing. As the current is changing, the magnetic field is changing. As the magnetic field changes, then you have, if you have a magnetizable material, its little magnetic domains are changing. But it takes energy to cause those magnetic domains to change. And it takes a little time as well. And so the fact that it takes some energy to change those domains means that you can't just replace mu aught with mu for whatever material you put in the core. You have to do some more adjustments to the equation. As a good approximation, that would be correct, but it's not a correct equation. So that's why I'm not going there. But if you put something like iron in instead of air in your inductor, you'll greatly increase the inductance because it's more magnetizable. So that's the equation for the physical inductance. You make a coil, you can determine its inductance by those measurements. So we have a group that's who's making the Tesla coil? Okay, so the back table with a few in front. They're making a Tesla coil. They're going to make a big solenoid. And they will know how many turns roughly they made. They'll know the length of it. It's going to have air in it probably. And so they can calculate what the inductance should be for their coil. And it is important to the operation of the Tesla coil. Now, sign conventions. Sign conventions are really important when we do circuits. For lab on Tuesday, we're going to be doing an AC circuit that involves capacitors and inductors. And based on the equation that we just saw, that is that the induced EMF is equal to minus. Okay, I better come up here. The induced EMF is equal to minus L delta I delta T. We need to make sure we have ourselves a sign convention that's going to work. The first thing we do with our sign convention is say, Okay, this minus sign, while it had a reason to be there, I'm going to erase it. And now you're probably like, well, that's no fun. You just went through all of these derivations. I can see why the minus sign was there because it was there in Faraday's law of induction. But why was it there in Faraday's law of induction? It was there to remind us to look at Lenz's law to determine what direction we were going to make the current. And for an inductor, if you wrap the wires to the left, you're going to have, a different magnetic field direction. If you wrap them to the right, you have to apply Lenz's law to determine how things are actually going to play out. So we drop it off and say we're going to set our sign convention without that minus sign. And so here's our sign convention. I'm only going to highlight picture A. If we have increasing current, that is if delta L over delta T is positive, then we're going to have the arrow for current direction and the signs for positive and negative on the inductor is shown there. Now, when you look at that picture, how does that compare to the sign convention for a resistor? If that was a resistor instead of an inductor, where would you put the positive and negative? Same or opposite? It's actually the same. The current goes into the positive side, comes out of the negative side in a resistor. You have energy lost as the current goes through. And if you have increasing current, it's going to be the same thing. Energy lost as the current goes through. Why would energy be lost as it's going through if the current's increasing? It's really easy to answer. If the current's increasing, what is happening inside of a coil? Current in a coil makes what? Well, we're assuming that there's no energy loss to heat. Well, it makes a magnetic field. And if you have more current and increasing current, what happens to magnetic field strength? It's increasing. The energy that's being lost is going into increasing the strength of the magnetic field. So you're taking energy from the current and putting it into the magnetic field. Hence, an inductor is storing energy in the form of a magnetic field. Remember we said a capacitor stores energy. We had two different ways that we could say it. We could say it stores energy in the form of a charge separation, or we could say that it stored energy in the form of an electric field. With the inductor, it's storing energy again, but in the form of a magnetic field. So inductors and capacitors, now we see a real similarity. They're both energy storage devices storing energy in fields. Now, if the current is decreasing, of course, that changes the sign. That's why there's the second picture. I'm focusing on this one because that's how we draw it in our circuits. In your circuits, you identify the direction you're considering positive for current. Even if it's an AC circuit where you know the current's going to be changing directions, you identify the direction you consider positive, and then you identify the positive and the negative sides of each item. And so we'll just use that sign convention. Okay, question number 1. What's the unit of inductance? All right. Okay, let's start at the top. What is ohm a unit of? That's the unit of resistance. Reactance and impedance. We've only studied resistance so far, but the ohm is also the unit of reactance and impedance. And we'll get to reactance real soon. Next one, the coulomb. What's that the unit of? Electric charge. The Faraday or farad, what's that the unit of? I heard somebody say capacitance. Capacitance is in farads. Then we get to the Henry, and that is indeed inductance. These two are not units in physics. Clerk is James Clerk Maxwell's father's last name. James Clerk Maxwell's father was given an additional title of Maxwell. It was another family name that was bestowed on him. And so we usually talk about James Clerk Maxwell and Maxwell's equations, but his last name was originally Clerk and became Clerk Maxwell. So I like to make a deal out of just as kind of interesting, hence the two names. Now, I mentioned that inductors store energy in the form of a magnetic field. And we know our equation for power is voltage times current. So the power in an inductor is going to be the voltage drop in the inductor, marked here as the EMF, times the current. So I'm going to say, okay, if that's the power is the energy per time. How much energy is required to build up to a certain current in an inductor? So my average power, well, if I increase the current at a constant rate, so I'm going to have the current as a function of time is a constant rate, hence it's going like this. Then I can say that the average power is going to be 1/2 of the peak voltage times current plus 0, right? Because you're going to make a triangle when you do the voltage times current equation. Or the, well, if that's the case, let me just show you. If you do the voltage versus current, that graph also looks like this. And so this here is adding up all of the voltage and current necessary to get there. And so the area there that I hashed is going to be 1/2 Emax Imax. And so that's why I have this here, 1/2 times the voltage times the current. And then using our relation, and you'll notice once again the minus sign was dropped off in the next line, to substitute for the voltage. So just replaced in parentheses there, that's the voltage, L change in I with change in time. That gives us an equation for the average power that was put in. Well, power is energy per time, so how much energy was put in if that's the average power? If power is energy per time, how do I get energy from average power? I have to multiply by time. So I take that average power, if I multiply it by delta T, I'll get how much energy was put into the inductor. So the potential energy, how much energy was added to the inductor, is power averaged multiplied by change in time, which is going to be, get to the end, 1/2 Li squared when you put all of your values in. So the energy stored in an inductor is 1/2 Li squared. Remember, for a capacitor, what was the relation? Look, I had the word capacitor instead of inductor there. For a capacitor, what was the relationship? Out of 1/2 CV squared. So again, we see a very clear similarity in the equations. The capacitor stored energy in the form of an electric field, and the energy stored was 1/2 capacitance times voltage squared. The inductor stores energy in a magnetic field, and its energy stores 1/2 the inductance times current squared. So it's a very similar definition. It's just one depends on the voltage, one depends on the current. Well, with the capacitor, we then use this to calculate how much energy density we have. That's how much energy per unit volume do you have if you have an electric field present. So we're going to do the same thing now for an inductor. Calculate how much energy you have per unit volume. Remember, the inductor has this equation. Divided by L, wasn't it? I am pretty darn sure that's divided by L. See right there? Divided by L. Don't know how that slipped past me. Let's say I did it last night, late at night. So that means that the potential energy 1/2 inductance times current squared is going to be 1/2, put in the value for inductance, times current squared. The volume of the inductor is area of a circle, pi r squared, times the length. And yeah, well, one of the two places I made a mistake, and I'm pretty sure, that I have a mistake here. I have to go back. I know this is the correct answer, but I'll have to go back and check what I did with the length there, because the length does need to cancel out. But the energy per unit volume is proportional to the current squared. Why is this important? Well, the current is going to relate to the magnetic field. And, oh, okay, there's not a mistake. I figured it out. Lowercase n is the number of turns per unit length. And so if you make the substitution, n squared is capital N squared over L squared. Well, I'm going to have to multiply both sides by L then to get the equation we had before. So, okay, there's no mistake. I don't have to feel bad. It was using a different unit or a different symbol. So if we calculate the energy density in terms of magnetic field, knowing that the magnetic field is mu watt N over L I, or mu watt lowercase n I, then that means that current is equal to magnetic field over mu watt N. And so that was substituted in for current there. This equation, once again, is an important equation. It's an important equation when we talk about electromagnetic waves, which is the next topic once we finish AC circuits. It's important because electromagnetic waves are transporting energy in the form of electric fields and magnetic fields. And so we need to have a way of understanding how much energy is being transported based on the strength of the fields. Why is this an important equation? Because it'll allow us to calculate the energy transported by electromagnetic wave. That's why it's important. Now to how we use these in circuits. The first circuit I have here is a transient circuit again. A circuit where I have a resistor in series with my inductor. And I have a switch. Now, when I flip that switch, it's going to start to have current. But there's an important rule. What's the magnetic field in my coil if there's no current? 0. The magnetic field cannot go from 0 to something else instantly. It has to build up continuously. But the magnetic field we've just seen is proportional to the current. So when I flip that switch, the current can't instantly jump. The current has to start at 0 and work its way up. So when I flip this switch, I know right off the bat that if I graph current as a function of time, at the instant I flip the switch, the current's going to be 0. But what's going to happen to the current over time? Is it going to stay at 0? No, it's going to grow. Is it going to grow quicker early on or quicker later? It's going to grow quicker earlier. So we can say the current's going to have to do something like this until it asymptotes to a maximum value. Now, how do we calculate these values and the equation that describes them? Well, initially, there's no magnetic field in that inductor, but we will have no current. So if initially current is 0, then voltage resistor initially is equal to 0. What's the voltage drop going to have to be across the inductor? If I close the switch and they're both 0, I would have, using Kirchhoff's voltage law, the EMF minus 0 is equal to 0. That's not possible. So what does it have to be? I'm very thankful that you answer something. What will it have to be then? It'll have to be the EMF that we start with. Now, I had implied here that I'm putting my current going out of the positive. And so I know that my VL0 is equal to L delta I delta T at time equals 0 is equal to the EMF. So I can calculate what the rate of change of the current will be initially. As I can calculate the change in current over change in time initially is equal to the EMF over L. And then over time, it's going to drop. Well, guess what? You use calculus to solve this problem. And it's not that hard to do the calculus. But what we get is exactly the same set of equations we got before. We have the current is equal to this. If time equals 0, e to the minus t over tau is 1. And it'd be I0 minus I infinity plus I infinity. And the voltage we have exactly the same set of equations for the voltage across the inductor and the current through the inductor as a function of time. But there's one wee little difference. That one wee little difference is tau. What was tau if it was a resistor capacitor problem? We called it the blank blank constant. Yeah, RC, time constant. So for a resistor and capacitor, tau was RC. For the inductor resistor, tau, I believe, is L over R. I'll be really embarrassed if we go to the next slide. It's R over L. But your time constant has to do with the inductance and the resistance now. And so, yes, the graphs, the waving of hands, the tau, L over R. Is that what I wrote? Good, good. I like to be right. It's better than being wrong. So what we have is an exponential change, once again, for the voltage and the current. Just like with the capacitor, except for now, with the capacitor, you had the voltage could not jump on the capacitor instantly. With the inductor, it's the current that cannot jump instantly. So that's the fundamental difference. Now that current can't jump instantly is kind of important for switches. Let's say you have something like an electric motor. An electric motor is made by having a coil, right? Make magnetic field. And so you have that coil with current going through it. When you turn the switch off, the current just can't instantly stop. So what that causes is a little bit of arcing that's going to occur when you turn off the switch. And thus, you have some problems with switches for inductors. And oftentimes, they make switches that they call make before break, where you connect across before you break the first connection to avoid that arcing. But if you look at the voltage, like if you have a DC motor, direct current, and you turn off the switch, you'll see that the voltage goes when you turn it off because of the switch being, you can't stop the current instantly in the inductor. And so it's arcing across the switch as you turn it off. All right, another question. An inductor in an LR circuit stores energy and then returns it. How does it store energy? Oh, you're right. It does say not. Okay, now it's open. Campus-wide, we're having lots of problems with the software. It's the manufacturer's fault. Okay, Ashley, give us an explanation on this baby.
I'm thinking that the magnetic field is right. It's not what I put. I just had remembered us talking about electromagnetic waves, so I chose C. But I'm sure that it's being.
You're sure that the majority is right?
Yeah.
Now, it turns out that the majority is right,
Yeah.
but that's not a good way to judge. You know, the majority of people say that, you know, Christianity is the wrong religion. Doesn't mean that we give it up because that's what the majority says. So, why would it be magnetic field? You have current going through here, and that current creates what in a coil? It's going to create a magnetic field. That's why it's storing energy in that magnetic field. The current creates the magnetic field, When you stop forcing the current, you still have that magnetic field, and then the magnetic field returns the energy by creating a current as per Lenz's law, or as Faraday's law. So the magnetic field drops and produces a current as it drops until you give it all back. So the correct answer was in the form of a magnetic field. Now, we talked about the electromagnetic wave. It's important that we have both the electric field is energy for a capacitor and magnetic field for inductor, because electromagnetic waves are storing energy in the electric field and storing energy in the magnetic field. And so we have to take both of those to calculate the total energy that's being transmitted by the electromagnetic wave. Although it turns out there's a fixed relationship between the electric field and the magnetic field, so we'll look at one of them at a time. The other ones here were, distractors that nobody was distracted by. Good job. Let's move. I want to get to the AC circuits. This here is just looking at another case of, well, how do you make a circuit? This circuit has two switches that open and close in tandem so that you charge the inductor through R1 and then you discharge it through R2. And when I say charge, you're not charging anything. What are you actually doing? You're building that would be charging. You're building a magnetic field. So you're building the magnetic field from that battery, and then the energy is going to be dissipated through R2. And so just like with the capacitor circuits, if you're using the circuit, you look at what resistance does the inductor see. In the charging picture, the inductor sees R1. And so you're going to get L over R1 for the time constant charging. When it's discharging through R2, so you'd have L over R2 for the discharging time constant. Hence, you can have a different time constant when you're charging versus when you're discharging. Now the comparison, because this is really a crux of the work today. The comparison between capacitors and inductors. So the voltage for a capacitor is proportional to how much charge you have on the capacitor. In the inductor, it's proportional to the rate at which the current is flowing, right? Very different things. The charge separation versus the rate of current, the rate at which charge is coming in or going out. For a capacitor, the current, it says can. Okay, I thought it was cannot. It's correct. The current can change instantly in a capacitor. So you have a capacitor that's really charged up. As some of you saw, you take that capacitor and you short across it once it's charged, and what happens? If you short it, what's the resistance between the two ends? Approximately 0. So what's your time constant if you have RC time constant and R is 0? 0. So you have approximately no time constant. It discharges instantly. You go from 0 current to a massive current with a capacitor. With an inductor, that's not possible. The current can't jump, but the voltage can. So with the inductor, when we went to charge it started with no voltage. You connect the battery, it goes to voltage equal to the EMF, and then that voltage will drop. So it can have a discontinuous change in voltage, but not current, whereas the capacitor can have discontinuous change in current, but not voltage. Then the situations when voltage is 0, when current is 0, are opposite of each other. Energy stored in the form of electric field versus magnetic field. I said that's super important. And the time constants, RC time constant versus L over R. These equations are fundamentally the same equation. And you ask, why aren't these equations exactly the same if I wrote them exactly the same? The reason that they're not exactly the same is because I use the voltage at time equals 0 and the voltage at time equals infinity, and the current at time equals 0 and the current at time equals infinity. I use that for my form because that's universal. It always applies, whether it's an inductor or a capacitor. So for any of these, I could have said I is equal to I0 minus I infinity. Come on. E to the minus T over tau. And V is equal to 0 minus V infinity. E to the minus T. So those equations are going to be correct whether it's an inductor or a capacitor. And finally, yes, question.
Just to make sure, so the capacitor is the one that doesn't affect the current, it affects more the voltage then?
The capacitor, I mean, both are going to have a voltage and current relationship. But the capacitor is storing charge separation. And so the voltage is proportional to the charge separation. The inductor is storing a magnetic field, and you have the voltage is proportional to the rate at which the current is changing. So there are different relationships for them, but there's still a voltage-current relationship. Okay, so problem. An electromagnet has an inductance of 15 henries. The resistance of the windings is 8.2 ohms. Treat the electromagnet as an ideal inductor in series with a resistor. Kind of convenient. The resistance in an inductor is never going to be actually 0 because you have wires. So inductors are not ideal in practice. You'll see that in lab. It's not going to be an ideal inductor. But we're treating it as ideal because, hey, we're learning. When a switch is closed, 24-volt DC power supply is connected to the electromagnet. So here's the circuit. What is the ultimate current through the windings of the electromagnet? That is, after a very long time, what will the current be? So when you look at this circuit, let's start with what's the initial current through the inductor going to be? It's what? It's not asked because it's assumed that you know, but nobody's answering, so it's good that I asked it. What did we say about the current through an inductor? It cannot instantly change. So before the switch was closed, the current was 0 because there was no power supply. So it's going to have to remain 0 at the instant that it closes. So that's our initial current. That's our I0. The question asked us, what's I infinity? What's the current after a very long amount of time? After a very long amount of time, what's going to happen to the current? Is it going to be changing or is it going to be constant? After a very long amount of time, the current's going to be constant. The voltage across the inductor is proportional to the change in current. So if the current's constant, what's the voltage across the inductor going to be after a very long amount of time? 0. So the voltage across the inductor after a very large amount of time is 0. Hence, all of your voltage drop is across the resistor. And so VR is equal to IR. That means I infinity is equal to the voltage of the battery over R. So that's the first one. That's what the current will be after a very large amount of time. Now, we could put in numbers because it gave us numbers, but since I only have a minute, I'm not going to. Second question, how long after closing the switch does it take for the current to reach 99% of its final value? So we're going to have I of T final is equal to 0.99 I infinity. And we need to find T final. Because we have no time, I use my equation, I0 minus I infinity, e to the minus t over tau plus I infinity. And since I0 was 0, then I just have 0.99 is equal to minus e to the minus t over tau plus 1. Now I can subtract 1 from both sides, and I'll have minus 0.01 equals minus e to the minus t over tau. Make them both positive, take natural log of both sides. Oops, no e. Therefore, t is equal to minus tau times minus 2. Oh, wait, that's natural log, not log base 10. And then you just have to put in your numbers. Tau is L over R, and put it in the calculator. Okay, have a happy Sabbath.